Sorry about the delay on this video. Finally getting it out to you. I completely had to re-record it. So there you go. We're going to be looking at electric power and household circuits. So the kind of framing device for this stuff is if you imagine looking at something like an electricity bill. Now, this is a photocopy of an old electricity bill from 2018. So the exact parts of it aren't exactly the same of what you might see on a bill today. In fact, the bill that might be coming to your house, whoever is paying that electricity, whether it's included in rent or a separate charge, might just be emailed, which mine is that I get at my place. But one of the questions you might ask yourself is, what are you actually paying for when you're paying for electricity? Are you paying for electrons, for volts, for current, for watts? What are you paying for? Well, it turns out you're paying for energy, which are measured in kilowatt hours by the electric company. And we'll get back to what all that is as we go. But essentially, it's kilowatts, watts being a unit of power multiplied by time. And so what we want to do is we want to get to the idea of electric power in circuits and electric energy. We know that the voltage has something to do with energy because it's defined as joules per coulomb. So we'll get to that. And then kind of think about how common household circuits, the kind of stuff that are in the place you live and the buildings you go into, right? If you ever plug in your charger at school, this is the kind of circuit. And then we're going to talk a little bit about this idea of power and brightness of light bulbs, which is an interesting connection. So the first piece of this is just electric power. Well, power is always defined as the rate of energy conversion over time. Or work done over time. And so when we're talking about electric power, we're talking about the rate at which electrical energy, which is what the battery or other device, the plug in the wall, the power plant, sort of generates this electric potential energy. And then the rate at which that is transferred to other things to be transformed into other types of energy. 100-watt incandescent light bulb, which you may or may not have this in your house. I don't have a lot of incandescent light bulbs left at my house. Most of them are LEDs and fluorescence, but you get the idea. These are very simple in construction. A current flows through the filament, it gets hot, it glows, it gives off light and heat. So a 100-watt light bulb, that tells us not exactly how bright it is, but we know that it transforms 100 joules every second of electrical energy into light and heat. Power is measured in watts, joules per second. But we also know that voltage is measured in joules per coulomb and current is measured in coulombs per second. So if we multiply the power, or we want to find the power of an individual element in an electric circuit or a whole circuit, we're really taking the current times the voltage, joules per coulomb times coulombs per second. You can check out those units, and we see that we get joules per second, which is the watt, which is the amount of energy energy per second or power that we're dealing with. This equation, however, is not always convenient. It's not always something that we measure both the voltage and the current. We can only measure voltage and current of a given circuit when the circuit is running. But we might know something about the circuit, and we happen to know about Ohm's law. So if we combine Ohm's law and the power relationship, we could say, well, if you replace voltage with current times resistance, or if you replace current with voltage over resistance, you can come up with these two other relationships, I squared R or V squared over R. V squared over R is particularly interesting because if you have, say, a 9-volt battery and you have a certain amount of resistance, you can predict how much power will be used, dissipated, converted by that object, right? And when we talk about power dissipated by a resistor, we're really talking about heat. The thermal energy converting electrical energy to thermal energy. These equations are valid whether it's alternating current, which is what comes out of the plugs in your house, at school, etc., and DC circuits, like the things that come from batteries, which is what we are playing with our Castle kit. So when it comes to electrical energy, we said power is the rate at which energy is transformed. So if you wanted to find the total amount of energy used, you would multiply the rate at which power is being transformed by time to get energy. And so our standard SI unit would be the joule, which is a watt times a second, because a watt is a joule per second. But, and this goes back to the original thing, we sometimes use bigger units like kilowatt hours, megawatt hours, gigawatt hours, that kind of thing, because a watt is actually not that much, right? A single watt of electrical energy You need 100 of those just to get a 100-watt incandescent light bulb. And even your low power devices, right? If you look at your phone charger, if you were to pick up, like I have a computer charger here, adapter, you probably can't see it, but on this it says 30 watts, right? That's how much it can use to charge my entire computer. And if you look at a cell phone charger, it might be 5 or 10 watts or something like that. So it adds up quickly, right? You've got appliances in your house, so 1,000 watts, a kilowatt multiplied by an hour is sometimes a much easier unit to use. So let's do a little bit of an example here. If you have an outlet in the US, it generally is about 120 volts that's being provided. It's 60 hertz AC current, which means it's in a wave changing direction 60 times a second, 120 times a second, 60 times a second. It goes through a full cycle. How much current does a 60-watt bulb draw? Well, if we know that the power and the voltage, we can find the current, 0.5 amps. But we might ask ourselves, well, what's the resistance of this bulb? Because this is an interesting thing. The watt rating of a bulb is only valid for a particular voltage. And so if you were to look at an incandescent light bulb, in addition to saying maybe 100 watts, it probably also says on there 115 or 120 volts, because that's essentially the US voltage, and these products are sold in this country. In Europe, the standard is about 220 volts, as opposed to 120 volts, 220, 240. So things are a little bit different there, and we'll talk about that in a second. But we can calculate that this is a 240 ohm light bulb, and the resistance is actually the fundamental characteristic of this light bulb. That is the thing that doesn't change. I mean, sort of with heat, as all resistive elements can be affected by how hot they are. But the resistance is based on the materials and the construction of it, and doesn't have to do with which voltage it's connected to. So if we take that same bulb to this, theoretical light bulb, and we take it to Europe, where it's a 220 volt, 50 hertz current. The 50 hertz, 60 hertz doesn't matter so much. It's more the different voltage. What stays the same? Well, the only thing that really stays the same here, right, is not necessarily the current or the power, but it is the resistance, because that depends on the physical properties of the bulb. It's the same physical bulb. So in Europe, then, you would calculate the power as V squared over R, 202 watts. So the 60-watt bulb on a 120 volt circuit will give you 202 watts on a 220 volt circuit, which is an important distinction. So whenever you get a power rating, if someone says, oh, this is a 60 watt, this is a 500 watt thing, that depends on how much voltage it is connected to. So it's not just enough to say what the power is. You could use this light bulb, but you might actually run too much current through it. For it to work, the light bulb might burn out, so you might need some sort of an adapter. So back in your house or your school or whatever building you're in with an electrical outlet in the United States, if we want to turn on several devices in the room, we might ask ourselves, how are these actually wired? Are they in series or in parallel? Well, if you imagine what's going on with a series circuit, the more you add, the bigger the resistance, the lower the current, and each of them has to split the total voltage as you go and do the loop rule around. That's not really going to be good. If you keep plugging in 100-watt light bulbs that all expect 120 volts, but they're now getting a third of that, that's not going to make them as bright as you wanted. So we use parallel circuits, and that allows you to turn something off, unplug it, without it affecting anything else. Every device gets the same voltage, and the current will be whatever it needs to be based on its resistance. So if we imagine a situation like this, maybe there's a 60-watt bulb on in the kitchen and a dishwasher, and we are told that the dishwasher draws 4 amps of power when connected to this 120-volt circuit. We find that it has a 480-watt power draw. That means 480 joules every second while it's running. That's probably on average something like a dishwasher, right? Cycles, and it's pumping water, and it's heating water, and it's spraying things, and then sometimes it's in a low cycle. But that's on either maybe it's an average or a peak power rating. So what is the total power of this circuit? Well, whenever you have multiple devices all connected in parallel, so you know how much power they each are using, then you can just add them together, right? 540 watts of power, 60 watts plus 480 watts. The power just adds. Energy and power are scalars, so we're not worried about plus, minus, etc. It's just the total power of the circuit. So what happens if you keep adding things in parallel? Well, we know that if you keep adding them in parallel, the total resistance will go down and the total current coming from that power source will go up. And so in the case of your house, this is not from a battery, it's from the electric company through an outside connection. The specifics of are not something we're going to get into here. But if you keep adding and adding them, the total current increases. And so we could ask ourselves, well, what's going to happen? Is there a point at which there are too many things plugged in? Absolutely, you can. You can either pop a circuit breaker, which is a spring-loaded bimetallic strip that gets warm and releases a spring when it gets too much current through it. Sometimes there's also magnetic ones, and then there's a fuse, which is basically a strip of metal encased usually in glass, where if the too much current flows, it melts and disconnects the circuit. So what do we do? Let's think about this. If every single one of these is running, will it blow a 15 amp fuse? You notice that the fuse is in series with the power, so all the current that goes through each of these devices must go through the fuse. The total current is the total power divided by the voltage, which gives us about 12.8 amps, so we're okay. It's not going to blow the fuse. If we added one more, even 60-watt light bulb, that would be enough to blow the fuse. I guess that wouldn't be, right? No, that would be another half an amp, and we'd be okay there. Oh, good. So we could turn on one more light bulb. Why do we use fuses? Well, that's just because if wires get hot inside of a building, they might melt, which would be annoying, potentially bad, but certainly getting hot can do things like cause fires. We don't want fires inside the walls. So we can do another calculation here, and that's to think about that back to that electricity bill, right? We certainly aren't generating our own electricity very often. If you have solar panels, you are. But even so, they're usually connected to the grid, and there's a charge with the electric company. So we have the situation where you might want to know how much it would cost to run a particular thing for a certain amount of time. So maybe you turn on the dishwasher and it runs for an hour and you run it every day, and you turn on the 60-watt light bulb for an hour every day. I don't know why that's it, but let's just assume that for the sake of argument. Well, the energy you use is 0.540 kilowatts, 540 watts, times 365 hours. That's 1 hour a day for 365 days, giving you 197 kilowatt hours. And then you multiply that by the rate of 20 cents per kilowatt hour, giving you about $40 to run all those things for a year. So what about brightness? Right? That's all about power and energy. But the question we still have is, which of these quantities is going to predict how bright a light bulb will be? Or maybe more usefully, you see a brighter bulb that's brighter than the other. What thing is greater for that bulb than the other? You've already sort of seen, probably through your investigations, that a bigger voltage for the same light bulb would give you a brighter light bulb. And so is it just voltage? Or is there something else that matters? And so it turns out that really the thing that matters for figuring this out is power. It is power that matters for figuring out which bulb would be brighter, assuming they're the same kind of bulb, right? So two incandescent bulbs, the one that has the most power dissipated will be brighter. And power is current times voltage. So if all of these are identical, and you kind of imagine what would happen here, in the parallel circuit, both resistors or both light bulbs have the full voltage. So they can also have as much current as they need according to Ohm's law, and that will give you something fairly bright. Over where R3 and R4 are, together the resistance of this circuit is much higher, so the current flowing through them will be less than in R1 and R2's case, and so you will end up with less brightness. So P3 and 4 will have the same current and the same voltage because they're identical resistors, but that will be a smaller power than bulbs 1 and 2, which each have their own full voltage of the battery and can each draw as much current as they need. So what's the ratio of these? Well, it turns out that if power is V squared over R, we can kind of see that the voltage is cut in half for 3 and 4 compared to 1 and 2, and you end up with a factor of 4. So 4 times more power for resistor 1 than resistor 3. So it should be 4 times as bright. Now, of course, 4 times as bright is sometimes a little difficult to observe. You would definitely notice that it's considerably brighter. But what if the resistors aren't the same? And this is an interesting thing. What if you have, say, a long and a round bulb? which you've played with. You've actually built circuits like this in the Introduction to Circuit Lab. You might want to know which bulb would be brighter in each circuit. And this is a little bit harder to think about because you need to understand first which one has the bigger resistance. Well, we know that the round bulbs are brighter, or the long bulbs are brighter. One of them is brighter. Which one, right? Based on what's happening. So let's think about this. Voltage is the same in the parallel circuit. Power is V squared over R. And the bigger resistance, the smaller the power. So the round bulb has a smaller resistance, a lower resistance. So it will burn brighter given the same voltage as the long bulb. On the other hand, the current is the same for both bulbs in this circuit, but the current is smaller in this case than it was in the parallel case because there's two bulbs with this resistance. And so if the resistance is higher, then the power is higher in this circuit because they have the same current. So this case, the round bulb, will be less bright than the long bulb because it has more resistance. It has a bigger voltage drop given the same amount of current. So it's a little bit counterintuitive, but that's the way it works. If you think about it using Ohm's law and the loop and junction rules. So we have a lot of things we know about resistors and how they behave in circuits. We know their units, ohms. They kind of act like friction. They resist the flow. We know how to understand resistance of a wire based on the physical characteristics. We've got Ohm's law and a couple different ways of thinking about it. We can add resistors in series and in parallel. And now we've talked about the energy and power for individual circuit elements. All right, that's it. We'll talk a little bit more about all of this as we get together next week. Hope you have a great long weekend.